All right, so let's try to address this discrepancy that this K introduces in our problem using something that's known as cross-validation. Okay, so what is this cross-validation? The question that we were trying to answer was that can we use K equal to 1, because then it would answer all our problems. The trade-off that was happening between E out of G versus E out of G minus versus E CV, right? And so the discussion that's going to come up is actually applicable to any machine learning problem, but we are illustrating it with a regression problem, right? So uh, let's look at a very simple regression problem. So what we are doing is, let's say we have this data set and we are trying to fit a regression line. So I have like these 3 points, and because we are using validation, so I will like leave one out, right, and then fit the data using the other two. So let's say my data points are x1, x2, and x3. And so the very first time what I do is I try to fit like just these 2 points. And this is the one that I left out because I'm using validation. And so this is the fitted line here, right? And what I do is I will get the validation error as E1. So let's say validation error is E1. And by definition, the expectation of this is E out on G1 deficient or G1 minus, right? And because like this, if you think about it, this validation error, like in terms of the picture that we'll have, would be the difference here. Let's say this is going to be my E1, right? Because this is the point that I left out, and so this is my validation point. So that's how I calculate this E1, right? And so this is going to be, most likely, this is going to be wild because the error bar is going to be huge. But then that's fine. The other thing that we can do here is that let's again leave one out on the same data set. Leave one of the point out. Let's say this is the one that's left out, which is my x2. And so I'll have like E2 calculated here because my fitted line is something like this, right? And so again, I'll have some error calculated here. And so again, I'll have the expectation of E2. That will be the estimator for my E out on G2. And similar to that, I can do the same thing with the third point, calculate the validation error, and then get the expected value for E3 to be E out of G3 minus. Okay, so how is this like which of the three should we pick, right? And in cross validation, what we pick is that we pick all of them. So we are going to pick all of these error calculations, pick all of them. In fact, take an average of all of these. Okay, so how is that going to help? Now imagine all these G minuses, like G1 minus, G2 minus, G3 minus, all of these, right? They differ from my G, my original G, which would be calculated on the entire data, right? And they also differ from one another. But that difference is like, if we take each of these like errors calculated on their own, they might be wild, they might not be as good. But if we take the average, we can cancel out this wildness, right? So that's the fundamental idea behind the cross-validation error. So E of CV is going to be 1 over n, and then the summation of all of these errors, right? Because I can somehow be able to cancel out the effect of the wildness for like that was applicable for 1 point by taking like the average of all these errors. So basically what I'm doing is what this signifies here is that this is also known as leave one out error, because I'm leaving out one data point, like this thing here. This is also known as like leave one out because I'm leaving out 1 point and then I'm calculating the error. For example, in this case, I just left out the point x and yn, right? And so on. So this is like the cross-validation error or the cross-validation estimate of E out. Okay, let's look at it, like summarize this, what really happened. So this is what we were trying to understand. With these 3 points, like I left this one out in the first case, then this one, and then this one, and eventually we came up with the cross-validation error, which was the average of all of these errors. So like intuitively speaking, you can see that I'm like really with this cross-validation, this idea of cross-validation, I'm really trying to include like everything in my final estimate, right? Because I'm just like leaving out one point and then calculating the error on the rest and doing that for every point, right? So this is what we call the ECV, or the cross-validation error, and it's an unbiased estimator of E out of G minus. Okay, so then what next? Well, we come to this theorem, and let me state that theorem here, which is that the expectation for, like, let's assume we are calculating it for different data sets, right? So the expectation over all data sets of size n of E of CV is equal to E out for n minus 1. Now notice why there is this like n minus 1 coming in there. So basically what we're saying is that the expected value of ECV is exactly E out n minus 1. This is true because for each individual validation error we are calculating it, right? We are getting the average of for each individual error. And so this is the, basically what I'm saying is that this is the this ECV is the unbiased estimate of E out n minus 1. Okay, so like what is the relationship between this ECV and E out in general? Like after having learned with endpoints, typically we can say that this E out of G is less than equal to ECV that we calculated like with the average of all the points. Okay, so how reliable is this ECV? How good or how wild can it go, by the way, right? And so like, can we elaborate a little bit on this relationship? So, well, yeah, we can. And based on like whatever knowledge we have of the theory, we can say that this E out is again less than equal to ECV plus some term that is of the order square root of n. Why? Because we took average of n points or n things, or like whatever we would like to call. And these n things are those small e's essentially. So those n's are nothing but these like E1, E2, E3 up to En, right? Because we were leaving one out and then calculating the error. So this is what this signifies. Now these n things are not completely independent. This is something that we need to know. And why isn't that like creating an issue? That's because, first of all, let's understand why these are not independent from one another. Why are they not independent? So E1, if you remember, was calculated and we got G1 minus, right? So it was calculated by leaving out X1, Y1, right? And so we got G1 minus. Similarly, we used E2 and we left out X2, Y2, and we got G2 minus, and so on, right? So here E1 was calculated by leaving this X1, Y1, and then this G2 minus, right, was calculated when X1, Y1 was there in the data, right? So this depends on X1, Y1 as well, although in a subtle way, right? So they are not completely independent, and so we can assume that they are almost independent, and so that's the assumption here. You assume that they are almost independent, but not completely independent. Okay, so overall, ECV, or the cross-validation error, is a good estimate of E out because we are just using k equals 1, and this is like one of the best known techniques in practice in order to get a reliable estimate of E out. Now in practice, now this was like one using like k equals 1, but in practice we use something that's known as k-fold cross-validation, sometimes known as n-fold cross-validation. So what is that? K-fold cross-validation. Okay, so cross-validation, why are we using it first of all? So cross-validation, as you can tell, is computationally intense. Like just think about it, like n data points. If we have n data points And let's say it's a regression problem. So you will essentially be solving n regression problems when you're leaving one out, right? So n regression problems. And so then one more for the final hypotheses, because we want to get the entire data in our hypotheses, as we said earlier. So basically what we're doing is we are having n+1 training sets, and we're solving those many problems, right? So then also add to that the complexity of the training and the data dimension. Like if the dimensionality is high, then you can imagine what's going on. So in order to resolve this issue of computational inefficiency, there is something that's known as k-fold cross-validation. For example, let's say it's tenfold, right? So sometimes it's tenfold cross-validation. And basically what's saying is don't leave 1 point, but maybe leave 10% of your data. So leave 10% of your data and then keep calculating the ease, but instead of like, let's say there were 1000 points, and then you're just like taking 10% at a time. So you're not going like 1000 plus 1 training sets, but you have a reduced number of training sets, right? So what's happening is, let's say I have like these divisions in my data, and then I will have like again G1 minus G2 minus, but the number of these will be considerably reduced. And what I'm doing is basically I'm leaving one out again, but that one is a section of the data and not the entire, like leaving 1 point and then calculating. So we are more efficient than the simple validation because we're doing the average of 10 deficient hypotheses. And in some case, we can even find like the ECV analytically, especially for regression. So we can find analytically for regression. And this, by the way, is given in the textbook, which I would encourage everybody to go in and have a look at it. And it's like in linear regression, you can actually get an expression for this cross-validation. And it's called, and sometimes we can even get like the cross-validation for different lambdas, which was my regularization parameter. And this is also known as regularized linear regression. So basically you can get ECV lambda 1, ECV lambda 2, and so on. And that helps us like pick the best lambda efficiently. So you can go to the book and actually check what's going on. Okay, so before we end this lecture, let's look at the practical application of how to see how to apply cross-validation on some real-world data. And again, because we've been using digits data, so I'm going to use that. So let's look at how we can apply cross-validation on digits data. And so first of all, let me write it down. We are looking at the application on digits data and see what's going on, right? So the first thing that we'll do is get features. So get features, in our case, it was symmetry and intensity. So let's get symmetry and intensity. That's the first thing. And then using like the classification problem, so most likely I'll be using PLA or pocket algorithm, depending on like how I want to proceed. Most likely this is the perceptron learning algorithm. And then the third is like what model do we want to apply to this problem. And what I'm doing is I chose, like, let's say I have this initial data, x1, x2. I chose to use a transformation. I chose to use a fifth order polynomial. So basically, when I apply the transformation, I'll have more dimensions here added. As we are aware, x1, x2, and so on, other terms max to the fifth order because we decided to use a fifth order polynomial. Okay. So having said that, we have basically 20 dimensions in Z space. That's the setup of the problem. And so what we'll do is we'll use a validation because we want to do model selection, right? So the fourth thing that we're trying to do here is model selection. And the best way to do that is that we'll have like these different models. Let's say like M1 was the model that had, and this is the max I went to, right? So the 20 dimensions. So maybe like M1 was having like one feature only, so 1 and Z1. And then M2 maybe had like two features, 1, Z1, Z2, and so on. Like I went until M20, right? And then I used cross validation to pick like my M of I, whatever that is. So the fifth step is like I use cross-validation to pick my model, which is going to be one of these out of these, and pick based on the number of like dimensions, right? That is also one of the important aspect when we are like doing model selection. Okay, so let's look at the results when we like did all of this and like what's going on in the digits data. So let's look at the actual experiment. The problem is 1 versus not 1, and so that's why you can see 1 is in like blue and the red dots are more red cross, and so obviously we have more data. And this was done, as far as I remember, on 500 points. So we have like randomly selected 500 data points on the training data, and the remaining are used as a test set. All right. So what's going on here is important. So this we understood. This is the X and the Z space, right? And so what's going on here is really interesting if you look at it. We see that the in-sample error, E in, is going down as is expected as we use more of the transform features, more complex. We do really well in E in, and we know why. Okay. Now, as we are adding more dimensions, like increasing the complexity of the model, the in-sample dropped. But if you look at the out of sample, it initially dropped, but then it began to increase. And you can tell why it happened because of the approximation generalization trade-off. That's like when it hit that trade-off, then it began to rise. And then there is this like ECV, this thing here. So what's going on there? Now we are doing this leave one out cross-validation error. We're tracking that. And as you can see, it's kind of, to a certain extent, mimicking the behavior of the out of sample error, right? Like somewhat, not exactly, but quite. And so if we have like two scenarios, like I can have two cases. One is that let me pick a model based on my E in. And then obviously I will pick the one with all 20 dimensions, right? But then the cross validation error curve, as you can see, ECV, is minimized somewhere between like maybe at 5 to 7, like somewhere here. I don't know, like 5 to 7 is looking as if it doesn't change, but maybe somewhere there. Let's pick 6, right? So let's pick 6 feature dimensions as the model. So now I have the model selected, right? And then let's look at what happens when we actually have the final results, like what is my classifier. So that's my goal. And well, on the left hand side you can see no validation, and based on my E in I used all 20 features. On the right hand side you can see I'm using cross validation. Based on cross validation I picked the 6 feature model, and then I'm doing things. Okay, so it's here, like on the left hand side, the one with no validation, you can see that this like there is overfitting. You can actually tell. And so E in is perfect, 0, right, as expected, but E out is huge, again as expected. Like it's clear that you have this classifier which is overfitting a few noisy points and just like blowing this E out up, I would say. Now what's happening here? Well, this is a reasonable fit, and in fact one of the best we have seen so far for this problem, right? It really fits in well, and then there is a perfect separation, and like as you can see here, of course there is this like slightly complex, and I wouldn't say slightly because we selected like 6 features, right? But then we knew that the ECV is the lowest there, and so that's what we selected, although E out is like, I wouldn't say very high, but it's really like, well, as it's extremely good, I would say, as compared to the E out that we are getting with the 20 features model, which was expected again because here a lot of overfitting is happening. And well, E in we have slightly greater than the one on the left, but that doesn't really matter because what we're looking at is how well it performs outside the data that we have, right? So first of all, yeah, overfitting is bad, as you can see, and cross-validation helped us in a way because it helped us pick a good model, right? So based on the cross-validation knowledge only, we picked the model with 6 features, sorry. Okay, so that's a comparison, and we can say for sure that validation wins, and validation wins in the real world as well. So because this is real world data. Okay, so that's it for this lecture. We are done with foundations in general. And we are all done with theory, I would say. In the next lectures that are coming up, we will be talking about, or I would rather say we will move towards application.